That was a nice little break. So today we're here to hear what 6 of our teams have been up to. They've been working pretty hard all year, and you can see them here. We've got an interesting mix, everything from one team trying to get everything they can out of water to one team trying to not make salty water, and all they do is make salty water. We've got others looking at graphite, which is at very high temperature, and others working on materials that don't like high temperature. So it's quite a diverse set of topics that we're going to hear about today. So here's our agenda. But first, I wanted to mention that this has all been very much a team effort, and this would not have gone anywhere near as well as it did without the help of our sponsors. A number of great Micron sponsors that have spent a great deal of time working with their teams and helping our students and mentoring them and so forth. I just want to thank them very much. Boise Cascade, our sponsors from there, have been also very helpful in working with our students very closely. And even Mike Hurley, who's from MSMSE and the Navy, who's been working with, sponsored another team on something near and dear to his heart. Thanks, Mike. And then some great faculty advisors, including Mike again, but Brian Jaquez, Ryan Pensack, and Scott Phillips all worked very hard to help our students succeed in what they were doing here. Well, I did a little bit. Just stay out of the way is what I did. Oh gosh, did I forget? I'm sorry, Steve. Steve, you should be there. My gosh. Yes, Steve was amazing, always. I always knew I'd forget someone. But there was also an instruction team that helped as well. Jen Millette from Writing Studies was phenomenal at helping our students develop writing skills with the reports as well as presentation skills. So very much helpful, very helpful. And then Shauna Potter is an adjunct that works with our students on teaching them professional skills that they may run into the need for. And then a lot of supporting people, Maya, Sophie, and our staff in the front office, Sierra, Linda, Ali Bay, Yasmina, and even Eric sometimes. But I want to thank everybody for helping all of this move forward. Okay, thanks. And now we can move on.
Awesome. Well, thanks everybody coming out. My name is William Cole, and I'm joined by my team members, Stefan and Dom. And we are super happy to present our research on the emissivity of graphite. Let's hop quickly into our sponsors. Our sponsors are from the Idaho National and even more. Awesome. Did you guys hear me well enough? Awesome. Figured I was loud. And Will Wenz, he is the chair of the non-metallic working group at INL, along with the technical lead for the Department of Energy's Nuclear Graphite Division. And our wonderful BSU mentor, Herold Ackler. Awesome, it works now. So let's give a little background on the nuclear industry. So the first generation of nuclear reactors that started being used in about the 1950s. The first reactor online was up in Idaho Falls, where INL is now. Currently on the grid, there's generation 3.5 reactors supplying about 20% of the US's electricity needs. Right now, we're working on generation 4 designs, and one big part about those designs is creating inherently safe and passively safe reactors. And one way people are going about doing that is using a lot of graphite in the core. Whether it's as a fuel form, structural components, or neutron moderators, there's a lot of graphite. Seen below here, this is a fuel form. Fuel pellets go in that guy, and this is a structural and cooling form. Those are just example components inside of the core. And it doesn't work again. Are we clicking around back here? Okay, let's talk about more of this passively safe and inherently safe stuff. So in an accident scenario, we lose cooling capabilities or something like that. We have to get a lot of heat out of the core, whether that's from latent reactions still happening or all of the heat that was in the core when it got shut down. Megawatts of heat needs to come out. And the only way for that to happen is for thermal radiation between graphite components and the pressure vessel wall. Things that can inhibit this heat dissipation is a function or a property called emissivity, and this can be hindered by surface contamination and surface structure changes as this accident is happening. Let's talk about graphite. Graphite is a carbon composite. It is polycrystalline and it has a lot of different crystal arrangements. It is also very dependent on processing. Graphite suppliers don't like to tell us exactly how each grade is processed, so we just get to do research on it. A lot of the mechanical properties is dependent on what orientation you're looking at them, along with the background processing. Seen here is two different graphite grades we looked at under an SEM image. There's a pretty big difference in the microstructure we observed, and that's just based on processing. So what are we looking at in our research project? We're looking at emissivity. Emissivity can range from a value of 0 to 1, 0 meaning it reflects and does not absorb very much electromagnetic radiation, and 1 meaning it is a perfect absorber. An example of this on the chart on the right is a couple materials with their emissivity values. Polished gold, like the heat shields in the James Webb Space Telescope, does not absorb a lot of radiation, and that's why it's used as a heat shield to keep the telescope cooled. And personal, or something you guys can probably relate to, black paint has a very high emissivity, so it releases a lot of energy. When you hold your hand over like a black car in the summer, you can feel a lot of heat coming off of it. That's an effect of the emissivity. Why do we care about this? So emissivity and emissivity is used in the Stefan-Boltzmann law. The power that an object can emit is directly proportional to the emissivity, the Stefan-Boltzmann constant, the area that the object has, and the temperature. This chart helps you visualize the differences in emissivity at a given temperature. We can see at about 1,000 Kelvin, the difference between 0.9 emissivity and 0.7. An object can radiate about 10,000 watts less. So how do we measure this emissivity? We use a pyrometer, which takes infrared radiation from a surface, and using a known temperature from a thermocouple, we can use the Stefan-Boltzmann law to backtrack for emissivity. Why are we doing this? Well, there's not very much published data on the emissivity of graphite above 500 degrees C, and modern reactor designs are having operation temperatures above 500. So what can affect this emissivity value? The chemical composition of the surface, along with the oxidation but the oxidation level of the graphite causing porosity and surface changes, along with temperature and surface contamination. I'll hand it over to Dominic to explain how we did this.
So to measure the emissivity of graphite, our team developed this technical approach. So it builds off previous work at Boise State and also improves the throughput and data confidence of data generated through our GEM system. So this is our basic experimental design. On the right, you can see a flange with a gas inlet, a thermocouple, and gas outlet. So in the center is where our graphite sample sits with the thermocouple inserted into it. On the left, you can see a zinc selenide window and pyrometer. Zinc selenide, also a high R transparency material. So the pyrometer and thermocouple work together to measure emissivity using ASTM E1933. So this is our GEM system. Essentially, at the start of the semester, we got this tube furnace. So here's our sample loader strategy. So the sample loader was designed using extruded aluminum to ensure smooth movement in and out of the furnace. So our graphite platform, also for that same reason, we need repeatable placement between samples within the furnace. So that was a fixed position granted by our graphite TC. We also made changes to the gas manifold and exhaust bubbler. So to modify the tube furnace, we added a different temperature controller with dual TC input and RS-45 communication. as well as adding RS-232 communication to our pyrometer. So the pyrometer is here, and you can see we added alignment stages to ensure precise and stable alignment throughout testing. You can also see an alignment laser to visually spot check where on the sample we are measuring infrared temperature. So this is our lab view software. It was added because each sample takes about 8 hours to run within the furnace, and we need 48 different runs. So with this software, we were able to control the furnace remotely and then export that data to a text file pictured on the right. So after modifying the furnace, we had to do a series of calibrations and qualifications. So to verify the accuracy of the furnace, we did a calibration with our black body calibrator on our IR sensor, and using a reference TC, we verified our graphite TC. So to verify precision, we also did a couple of tests. So temperature stability of the graphite sample at each temperature set point, and repeatability testing using the same sample. So we were testing 6 types of graphite, 0 to 10% oxidation with and against grain orientation. All samples were prepared at the INL, and SEM images were taken on 0% oxidation samples. So each sample was run 250 to 1,000 degrees Celsius, measurements all followed ASTM E1933. So some characterization was also done on select samples after we were done.
All right. We have tested 24 different samples with 2 different orientations, totaling 48 data sets. We've chosen ET10 against grain orientation to show. This chart shows the relationship between emissivity, temperature, and oxidation. What we see first is that emissivity increases consistently with temperature for every sample. And across the full range, there is some variation between samples, but there is no clear pattern tying that variation to oxidation levels. At lower temperatures, most values are relatively close with one lower outlier, and as temperature increases, the spread remains but follows the same overall trend. So from this initial view, temperature is driving the emissivity behavior, while oxidation does not show a strong or consistent effect. And at the start of the data collection, we ran one sample 3 times through, and we saw consistent data across all 3 runs, meaning we had very good repeatability that was within our uncertainty. And all samples follow the same overall trend. Emissivity increases steadily with temperature from 250 up to 1,000 degrees Celsius. This chart shows the relationship between emissivity, temperature, and oxidation. What we see first is that emissivity increases consistently with temperature for every sample. And across the full range, there is some variation between samples, but there is no clear pattern tying that variation to oxidation levels. At lower temperatures, most values are relatively close with one lower outlier, and that temperature increases the spread, but follows the same overall trend. So from the initial view, temperature is driving the emissivity oxidation, while oxidation does not show a strong or consistent effect. The full temperature range, there's some spread between the oxidation levels, but that spread doesn't follow the patterns. So overall, temperature seems to be driving the trend with little variance. Just go to the next one. Now, moving into analysis, we isolated the emissivity at 1,000 degrees Celsius and compared it across oxidation levels. The values range from 0.89 to 0.83 to 0.89 emissivity, showing some variation between samples. However, as viewed in the graph, there is a consistent upward trend with increasing oxidation up to 5%. After 5% oxidation, there's no observable trend as the change in emissivity values varies between samples. If oxidation were the dominant factor, we would expect a clear monatomic relationship, but that is not observed. And from these SEM images we took, we can see the differences in porosity and surface roughness between samples. This is an effect of oxidation. These types of features directly affect how radiation interacts with the surface, which can influence emissivity. So some of the variation in emissivity behavior is likely tied to the effects from surface structure and microstructural characteristics tied to oxidation. However, we were unable to make a clear connection between the structure and measured emissivity. So stepping back and evaluating the outcome of the project, we were able to successfully measure emissivity for several grades of graphite through all temperatures and oxidation conditions. The data set is repeatable and shows consistent behavior, especially at high temperatures. Going into the project, the expectation was that oxidation would significantly increase emissivity based on the data. The trend is strongly supported and isn't strongly supported. Instead, what we see is that emissivity varies, but does not show a strong or consistent correlation with oxidation. So the key takeaway here is that emissivity is not controlled by a single variable. Instead, it depends on a combination of factors, including surface temperature, including temperature of the surface conditions and microstructure. Yeah. And we'd like to acknowledge these people and organizations. Thank you.
We have a few minutes for questions. That one back there. Turn it off.
You have your percent oxidation values. How did you confirm those numbers?
Yeah, so the percent oxidation values was given to us by the IANL. The oxidation controls, or the effect of oxidation on the graphite creates porosity and mass loss. And the way they calculated the oxidation level was by the mass change from the unoxidized samples to the oxidized samples. So they weighed them before they oxidized them, and they saw how much mass was taken out, because the oxidation is a mass loss function instead of like a iron oxide type effect. So the mass loss directly tells you how much oxidation happened.
Second question. Can you go back to the emissivity plot as a function of temperature? There we go. So curiosity, what would, in your all's viewpoint, be a significant shift in emissivity to say there is an impact?
Impact of oxidation?
Yes, because I see a gap. Just curious, is that impactful enough?
So the way we went about figuring out if that was impactful enough is look at how much error we have in our readings. We had a lot of issues with calibration and error percents coming into this project. We are hypothesizing that each one of these values is roughly within the error bars of each other. So we can't see a big enough distinguishment from each data point to where we think that's the oxidation or the error we're seeing.
That's based upon hypothesis?
Hypothesis, yeah. We had a bunch of issues with our calibration and not knowing our exact error amounts.
Gotcha. Thanks.
Thank you.
One more?
Yeah, we're on a time.
Thank you, guys.
Good. Next up is the composites team.
Hello, everyone. My name is Joselyn, and I am here with my teammates Caleb and Danny. Our project was on determining the feasibility of upcycled wood-polymer composites. So first, we would like to introduce our sponsor, Boise Cascade, who has been investing in engineered wood products since the 1990s. They provide building materials and support across the United States and Canada, and have earned their spot as a Fortune 500 company. Lastly, we'd like to introduce Thomas Black, Engineered Wood Products Laboratory Coordinator, and Tyler Congleton, Product and Sustainability Engineer, who provided excellent mentorship and assistance with this project. And additionally, Dr. Scott Phillips, our faculty mentor, who without his support, laboratory, and equipment, this project would have not been possible. Boise Cascade has continuously optimized their manufacturing processes to minimize waste. However, two irreducible low to no value waste streams remain. On the left, we can see one of the wood waste streams. This is the protective lumber wrap that is used in transport and is made of polypropylene. On the right, we have our other waste stream, sawdust, created during the manufacturing process. The demand for wood waste increases annually, and in turn, the generation of wood waste also increases. Currently, 64 million metric tons of wood waste are produced annually. Additionally, approximately 28 million of this wood waste is treated, which means it contains a chemical wood preservant that contains chromium, copper, and arsenic, and poses hazards to human health and the environment. Boise Cascade, however, is already taking the important measures to ensure adequate sustainability measures when it comes to wood waste. The waste stream that is of more concern is the polymer waste. Currently, as we can see in graph A, over 0.5 billion metric tons of carbon are emitted annually due to the production of polymers. And in graph B, we can see that around the same is emitted from the polymer waste. So it's important to note that the vast majority of the CO2 emissions is due to packaging, leaving lasting effects on the environment. And in graph C, we can see that only a small fraction of packaging actually remains in use. This is why the upcycling framework becomes relevant. By transforming waste into a new material of higher value, Boise Cascade can turn their no to low value waste stream into a product that is competitive on the market while simultaneously increasing sustainability efforts. This ensures that the essential protective lumber wrap has an increased life cycle.
All right. And now for some background on composites. There are fiber reinforced composites, which composites in general are two dissimilar materials, the matrix and the reinforcement material, and they are bonded together in order to form new properties or to combine their properties. So the matrix is reinforced with these high strength fibers, and some common examples you see in real life are carbon fiber, fiberglass, and even cement. And there are particle reinforced composites. And then these use the polymer matrix, and they're reinforced with uniformly distributed particles. Some of these particle types can include ceramides, sawdust, and glass beads. And some examples that we see in real life are ceramic composites and wood plastic composites, which is what we are tackling. So we have a polymer composite material, which has a polymer matrix and a wood particle reinforcement, which in our case is sawdust. The industry standard actually use HDPE or PVC, and those are like from companies like Trex or TimberTech, and we are actually using exclusively polypropylene. So the reinforcement phase is supplied by Boise Cascade, and it's sawdust. It's supposed to boast a high stiffness and strength and improve the load bearing of the material. And it is a hydrophilic material, meaning it absorbs water easily. As for our matrix phase, we have polypropylene. It's a ductile material, it provides the structure, and it's a hydrophobic material. And it's also supplied by Boise Cascade, and this is one of their main waste streams. So we are looking to combine their properties, but these properties do depend heavily on the composition, the interfacial bonding, as well as the quality of the processing.
Thank you, Danny and Joselyn. And now that we've discussed a lot of the background information, we can begin to discuss how our group tackled answering the specific question, can Boise Cascade's waste streams be turned into a viable composite material? We accomplished this by chasing down three main objectives, those being developing a polymer wood composite using the specific materials that Boise Cascade provided, which are different than the other traditionally available composites. We evaluated the mechanical properties of those composites that were manufactured, and we wanted to analyze exactly how the recipe or the variation of the wood waste percentage impacted the composites that were manufactured. We did this predominantly through a technique called extrusion manufacturing. It's the most common form of manufacturing polymers, and getting it right was essential to our project because we identified that the single greatest impacting factor on a wood plastic composites material properties was the ability to manufacture it correctly and completely. Specifically, we accomplished this extrusion manufacturing by processing the 2 waste streams that Boise Cascade provided us, putting them in the hopper, which gravity fed the extrusion auger that were then heated, compressed, and metered into a die, or into our case, 1x1 board molds. The specific way in which we tackled this approach was by having 3 control groups and 5 variable samples. This allowed us to compare the wood plastic composites that we manufactured to an industry standard, to an upcycled polymer that did not contain any reinforcement, and finally to an upcycled or a virgin polymer, polypropylene, so we could evaluate the impact that upcycling might have had. The specific process that we used is we processed both the lumber wrap and the sawdust before feeding them into an extruder. We then granulated the extrudate and potentially repeated that process as needed to ensure complete mixing. Once they were fully mixed, we dried the extrudate one final time before feeding it into a final extrusion, where the 1x1 boards were then sectioned and planed according to ASTM standards for a 4-point bend test.
All right, and here are the results that were yielded from our testing. So here we have all our control groups, which is the Trex, the pristine, and the upcycled polypropylene, as well as our variable groups, which is the 5 through 40% wood weights. So here we see there's a trend that occurs as we increase the wood content. There seems to be a stiffer curve, which must mean a higher modulus of elasticity, which is recorded over here. And this is the table that we came up with. There are two data points. One is the actual modulus elasticity that was calculated for these materials, and the other one is the least squares fit to make sure that we are fitting the linear elastic region of the stress strain curves as best as possible, and that'll be explained later. But here we see that Trex exhibits about 1600 megapascals. Pristine and upcycled polypropylene have around the same modulus elasticity as well, around 1200 megapascals. And once we introduce the reinforcement material, we see a sharp increase in the modulus of elasticity. So we go to 1800 at 5%, 2200-ish at 10%, and 3800, a massive jump from the 10% to 20%. And at 30%, we peak at around 4700 megapascals. And then once we hit 40%, we then dip back down. So 30% was peak for us. There's a modulus of rupture, same trend occurring. That dip occurs after the 30% into the 40%. And the hardness testing, not too much that's different across all of the samples that we manufactured. There's like a noticeable hardness difference between the industry standard Trex and our samples. And how they were fitted, again, where it was through a least squares model or a linear regression model. I would just fit, take one point and then take another point, draw a straight line between them, and then fit it as best as possible to that region, and then determine the slope from that straight line. And then we would measure how well that fit through an R-squared score. The closer it was to 1, the better. And here's an example of it, of us including or excluding the toe region and excluding anything that was like nonlinear.
And unfortunately, it's not possible for us to discuss our results without also discussing some of the challenges that we encountered. Predominantly, we found that there were substantial voids throughout many of our samples, which have impacted our results. Predominantly, the accuracy of the MOR and MOE is unknown, as it's not possible to quantify the exact impact that these voids had on those specific numbers. However, the hardness data was unimpacted, as these the durometry testing was done on areas that were verified to be completely void-free. And ultimately, Throughout this process, we were able to improve the extrusion techniques that we were utilizing and refine our processing to eliminate voids as the project progressed, but we were unable to do so completely. This, however, doesn't impact the final conclusion of our project, which was determined using trends and comparison between different samples rather than any individual numbers, which have that unknown error in their accuracy. And so to provide that conclusion, here is Joselyn.
So we learned that despite the processing challenges we face, trends show that a direct correlation between sawdust, reinforcement, hardness, and stiffness exist. And future work should include an improved manufacturing control, like an industrial drying and mixing process, a vented extruder to try to minimize the void generation challenges. And although future work is needed to create and optimize wood polymer composite, it can be said that for Boise Cascade, that it is possible to create an upcycled wood polymer composites from their two waste streams of lumber wrap and sawdust. And these are our acknowledgements.
Thank you. Any questions?
Thanks. Great work. How did your test results on Trex compared to published data on Trex?
So the results that we had on Trex compared to the published data seemed to be about approximately the same. The MOR that we calculated was, I believe within about 10% of the published value. But ultimately, the reason that we wanted to repeat these experiments rather than use published data is because we wanted to compare exactly the same samples of exactly the same shape and geometry on our setup. And so we feel like the Trex testing that we did is actually quite accurate in terms of its overall individual numbers, as that did not have any voids because we did not manufacture the Trex, obviously. But yeah, so about within 10%.
And so you have polypropylene Trex as HDPE.
That is correct.
Or PVC.
It's HDPE.
And virgin HDPE or PVC compared to virgin polypropylene. Is that what you
No.
expect?
Not quite. So we did the pristine or the virgin polypropylene compared to upcycled polypropylene, because ultimately the goal here was to evaluate if Boise Cascade could make a viable composite material using the waste streams that they had. And they have polypropylene, they don't really have HDPE. And so even though a lot of the industry players currently use HDPE, really we're trying to investigate if we could use a different polymer and achieve similar results. So we were mainly focused on the behavior of polypropylene to evaluate it as a candidate rather than as like to evaluate if it was like the best option for whatever use case scenario that it may be used in.
I may have missed it, but what was of the two pristine and upcycled polypropylene, what did you use for your wood filling? Which one of those two did you use for your wood filling?
Could you elaborate?
Yeah. So you made a 5% wood sample, and there's only one line of data. So the polymer that went with that was either, I presume, pristine polypropylene, or it was upcycled polypropylene, but I can't tell which one.
Yeah. That's a good point. Yeah, we use the upcycled polypropylene.
Anything else? Well, thank you.
Hello, everybody. My name is David. These are my partners, Jacob and Joe. And our project is on charge trapping films and interfaces in 3D NAND devices. So we'd like to first thank our sponsor, Micron Technology. They're a semiconductor manufacturing company based here in Boise, Idaho, and one of the largest producers globally of memory technology. From Micron, we have Dr. Beth Wilneff as our industry sponsor. And from BSU, we have Dr. Stephen Hughes, our faculty advisor, who are both extremely experienced in surface analysis and thin film properties. So NAND flash memory stores data by trapping charge in a silicon nitride charge trapping layer. And during manufacturing, these layers are exposed to energetic particles that alter bond structure, trap density, and charge retention. Our work aimed to characterize how surface treatments change the electrical and chemical properties of these films. So to give you a quick idea of how NAND works, by applying a high voltage to the control gate, electrons can tunnel through the insulative layer into the charge trapping layer. When that voltage is removed, the charges are retained in that charge trapping layer. By applying a low voltage to the control gate, electrons may or may not tunnel based on the threshold voltage that is affected by the trapped charges. To remove the charges, you can apply a high voltage to the substrate to essentially pull them back out. So as these charge trapping layers get thinner, the operating voltage and power required decrease, which is a good thing, but the amount of available trap sites also decreases, which makes it harder to retain information for a long time. And any manufacturing step that alters the silicon nitride bond density, any manufacturing steps that alters this bond density and stoichiometry shifts both the trap depth and the spatial distribution of these charges. And because these processes are sequential, it's hard to know which process affects the films with what damage. So to quickly talk about the physics behind charge trapping, silicon dangling bonds are the primary source for both oxide and nitride films. In silicon dioxide interfaces, the traps are amphoteric and shallow, meaning only a little bit of voltage is required to get charges in and out, making them not very reliable for trapping these charges. In the nitride, the traps are in the bulk material. They're deep and spatially distributed throughout the film, requiring a lot more energy to get charge in and out. And so any process that breaks these bonds changes how long and reliably charge is stored. So we use several instruments to characterize our initial films. First, using ellipsometry, which measures the thickness based on phase and amplitude shifts of polarized reflected light. This can be fit to a model, giving angstrom level precision, and is also non-destructive. We use non-contact tapping mode AFM for surface topology, and we use KPFM to map surface potential, voltage potential difference, and modified work function. This tells us if there's charges trapped in the film or not. Finally, we used XPS to distinguish the silicon 2p peak, indicating elemental silicon, silicon nitride, and silicon oxide bonding states to track interfacial chemistry changes. To treat our samples, we used two methods. We used electron irradiation with an SEM. This E-beam generates electron hole pairs, releasing hydrogen from silicon-hydrogen bonds, creating more silicon dangling bonds. We also used argon bombardment via an XPS instrument, and these argon collisions preferentially sputter nitrogen, yielding a silicon-rich surface, inducing heavier physical damage. So the goal of this project was to determine the effects of sample modification on charge trapping characteristics of both the silicon oxide and silicon nitride films. To do this, we took preliminary measurements of our samples. We subjected our samples to surface treatments. We took post-process measurements as well, and then compared initial and final measurements. I'll now hand it off to Jacob to tell you how we approached this problem.
As David mentioned, we had three phases of our project. Our phase one was doing ellipsometry, AFM, KPFM, and XPS to determine our initial measurements. And then we entered phase two, which were our surface treatments of electron irradiation and argon bombardment. And then finally, we did our metrology again to get our final results, and then we evaluated them. So these were our parameters for our argon bombardment. We had 3 accelerating voltages and 2 time levels. And the way that we determined these were through trim simulations. So the long axis is 100 nanometers, and we use these simulations to qualitatively assess how deep damage would occur in our samples. The initial thicknesses of the films that we got were 120 nanometers, 20 nanometers for the nitride and 100 nanometers for the oxide. And so we wanted to assess damage mainly on our films and not on our substrates. And as such, we chose accelerating voltages that did not damage beyond, on average, 50 nanometers to do just that. Our electron beam parameters were based on dosages that could be encountered by samples through an SEM scan in industry. And our dosages went from 14 coulombs per centimeter squared to 64 coulombs per centimeter squared. It is important to note that the SEM that we were working with did not have a Faraday cup, so the we use the emission current of the SEM to estimate these dosages. As I stated previously, our pre-processing thicknesses were 20 nanometers for our nitride films and 100 nanometers for our oxides. And post-processing, these seem to have increased. We attribute this to a difference in NAK throughout the samples due to various native oxides and other contaminations on our films. In regards to the roughness of our samples pre and post treatment, they are basically atomically flat. The noise floor of the instrument and the mode of contact that we did for attaining this data is around 50 picometers. And as you can see on the axes, on the y-axis, our scale is in the hundredths of nanometers, which is within the noise floor of the instrument. So with regards to electron bombardment and argon bombardment, there is no significant difference in roughness pre and post processing on our samples. With regards to electrical characterization, there is a significant difference between pre and post processing for our nitride samples with electron bombardment, but there is not a significant difference between pre and post processing for our oxide. The same can be said for our argon bombardment, with a definitely more pronounced difference for our nitride samples. And this is in agreement with literature that we found about nitride being more sensitive to these processes than oxides. I'll now hand it off to Joe to continue analysis of our results.
Okay, so now let's take a look at the XPS result for the nitride after argon bombardment at 4 kilovolts. Red is before treatment, blue is after treatment. So as we see, the oxygen peak dropped significantly after bombardment, meaning the native oxide sitting on top of the nitride was removed. The nitrogen peak stayed, confirming the nitride film is still there, and the silicon peak increased slightly. So together, these changes tell us that argon exposed the true nitride surface underneath. For the oxide after argon bombardment at 1 kilovolt, the peaks before and after look almost identical. There is very little change in either the carbon or the silicon peak. 1 kilovolt was simply not enough energy to significantly change the oxide surface chemistry. Now for electron bombardment on the nitride, looking for all 4 peaks, the lines before and after sit almost on top of each other, so there is very little difference. So this tells us that electron bombardment did not cause a measurable chemical change in the nitride, but as we will see in the analysis, that does not mean nothing happened. Same story for the oxide after electron bombardment. The peaks before and after are nearly identical, so no significant chemical change detected by XPS for the oxide either. To connect everything together, for argon bombardment, XPS and KPFM are telling us the same story. The nitride surface chemistry changed and its electrical behavior changed too. The oxide showed much less change in both. And for electron bombardment, XPS showed no significant chemical change in either film, but KPFM detected an electrical response in the nitride. A few things are worth discussing. First, silicon nitride was more responsive than silicon oxide across both treatments, and the 2 treatments affected the films through different mechanisms. Argon changed both chemistry and electrical behavior, while electron bombardment only showed an electrical effect. Second, one challenge we faced was that our samples are insulating, which caused charge to build up on the surface during XPS measurements, and this introduced artifacts into some of our results and made them harder to interpret. And to conclude, this project showed that manufacturing-related surface treatments do change the charge trapping behavior of the films used in 3D NAND memory. And silicon nitride and silicon oxide did not respond the same way. And argon and electron bombardment did not affect them the same way either. For future work, there are three things we would consider doing differently. First, we would use doped wafers with a MOS structure, and MOS stands for metal oxide semiconductor, which would allow us to do CV measurements and directly measure trap density. Second, we would remove the native oxide from the samples before processing. So we start with a cleaner and more controlled surface. And finally, we would store the samples in a nitrogen purge box between steps to prevent them from reacting with air and affecting our result. And we would like to thank Micron Technology for sponsoring this project, and a big thanks to our industry sponsor, Dr. Wellneff, and our faculty advisor, Dr. Hughes, and everyone listed here for supporting us throughout this project. Thank you for listening.
Can you go to slide 18? What the heck is that right-hand side telling me?
So,
What's first of all, what's my y-axis?
yeah, that's the voltage potential difference versus gold. All of our KPFM samples were measured against a standard of gold. The main issue with using KPFM for these electrical testing is that this is done not only in air, but also this is against a reference. So this is not strictly a quantitative value of this is exactly what this sample is. This is against a reference of gold. So this also depends on the probe that is taking the measurement, which is what these error bars are, which is a combination of the error of the probes for both the standard and the sample itself. So these results should just be used for a qualitative assessment, not quantitative. All that to say.
So why do I have a zigzag effect on
Yeah.
the oxygen argon bombardment?
That's a great area for future study. Where we would attribute this basically to the probe and the exact humidity of the room. Since this is done at atmospheric pressure in air, there's a lot of temperature and humidity effect on the actual probe and the measurements at when they're being taken. So again, as this is qualitative, I think it's more apt to look at the difference between the pre and post treatment than it is to look between different samples.
Okay. One more question. Go back to your damage. Your simulation of damage. Yeah.
Yes.
Okay, what's my Z? I can't see the Z-axis. I'm an old lady. I can't see those numbers.
Yeah.
And which one did you end up using? 1 and 2?
So we did 1, 2, and 4. Our Z-axis is a count of ions found at that specific depth. So this is more like a count of ions and how far they penetrated into.
Oh, it's how far they penetrate. You are not actually simulating damage, then you're simulating depth of the argon.
Yeah, there was this software did have counts for sputtering as well, but the fluence that we did these calculations for was very, very low. So the counts for sputtering was also very low.
Not sputtering, but often when you say a damage simulation,
Yeah.
what I'm expecting to see is how many atoms you kicked off their site. But what you're saying is this is actually argon concentration.
That's correct.
Okay.
Anyone else? Thank you.
Good afternoon. My name is Brylee Rubio. This is Lucy Brown and Ryan Grove. And our project focuses on corrosion assessment and mitigation of additively manufactured and wrought stainless steel. This project is supported by NEEC, the Naval Engineering Education Consortium, which partners with universities to address engineering challenges in naval environments like corrosion in marine systems. This project is also advised by Dr. Mike Hurley and was in collaboration with a graduate researcher, Noah Montrose. Corrosion is a major issue in naval environments where materials degrade more quickly. 316L stainless steel is commonly used for its good corrosion resistance, and additively manufactured or 3D printed stainless steel can be used to make more complex geometries. However, welding is required to join the two in application, and when you combine these conditions, it can cause issues at the interface. So although additively manufactured and wrought stainless steel are the same compositionally, they have different microstructures. And welding introduces a HAZ zone or a heat affected zone, which is highlighted in red on our diagram, as well as compositional gradients. And this can lead to electrochemical imbalances at the interface, which can drive corrosion. So with this problem, first we looked at why stainless steel can typically resist corrosion. So 316L stainless steel forms a protective chromium oxide passive film, and it's able to self-heal in the presence of oxygen. This film is stable in many environments, but in chloride environments, it can tend to break down, and this breakdown becomes more likely when there's differences within the microstructure. Here we have one of our welded samples. On the left, we have our wrought. On the right, we have the additively manufactured, and highlighted in the dotted box in the middle is the weld interface. The wrought material has a lot more uniform microstructure, while the additively manufactured material has more defects like porosity and segregation. These defects can act as initiation sites for localized corrosion. As mentioned before, welding also creates a HAZ zone, the heat affected zone, and this is where the material doesn't necessarily melt and re-solidify, but it does get hot enough to change the microstructure. It also introduces a fusion zone, and this is where it's actually melting and re-solidifying. So the gist of this phase diagram is within varied positions of the weld, the material is heating and cooling differently, and this is leading to variation in the microstructure. It can also lead to chromium depletion at the grain boundaries, which can weaken that passive film and it can lose its ability to self-heal. So in order to address this, we are looking at a mitigation strategy. Specifically, we are looking at atomic layer deposition, or ALD. ALD can form thin conformal coatings that can coat even complex surfaces with rough features and pits. The schematic shows the ALD process where alternating precursors are reacting with the surface to create a thin film layer by layer. And after several layers, it can build a thin film that can uniformly coat even like the rough surface. So in order to analyze this, we use electrochemical testing. Specifically, we use EIS, or electrical chemical impedance spectroscopy. What it does is it applies a small AC signal and it measures the response. And if you look at a low frequency impedance, you can kind of decide how the material will be able to resist corrosion, where a higher impedance is more corrosion resistant and a lower impedance is more likely to corrode. And with that, we were able to define the goals of this project. Our primary goal was to assess the weld interface of the additively manufactured and wrought stainless steel. And our secondary goal was to evaluate whether the ALD coating was a promising mitigation strategy for resisting corrosion. So with that, we understand the problem. And our next question was, how do we evaluate this experimentally? So Ryan's going to walk us through what we actually did to keep driving this project.
Okay, to accomplish our goals, we first needed to prepare our samples. The schematic on the right, okay, all right, doesn't work. The schematic on the right shows how our samples looked after they were prepared. Each sample had a nickel ribbon spot welded to them with heat shrink tubing covering at least half of the ribbon to protect it from the saltwater solution. The nickel ribbon was used or was needed to make an electrical connection. Then the samples were mounted in epoxy to prevent galvanic corrosion between the nickel ribbon and the stainless steel. The diagram on the left shows the orientation of our welded samples, and the bottom side was our exposed surface side. We had two main sample groups, single samples which were not welded, and welded samples which included 3D printed welded to wrought and wrought welded to wrought. TIG welding with ER309 stainless steel as the filler metal was how they were welded. Each group consisted of samples being in the as received or polished condition. Polished samples were polished between 60 to 800 grit as to create a smoother surface. Two of the 3D to wrought samples, one as received and the other polished, had a 100 nanometer thick aluminum oxide coating deposited on them by ALD. All of the samples described were tested using this setup depicted in the slide. Our samples were submerged in 3.5 weight percent NaCl solution as to mimic seawater inside a plastic container. The lid had holes in it to hold the reference electrode and the counter electrodes in place. The samples were submerged in solution for about an hour before the first EIS test to allow for the corrosion potential of the samples to stabilize. The samples sat in solution for a total of 500 hours, which is equivalent to 21 days. EIS was run 4 times over the course of 21 days at days 1, 7, 14, and 21. This was to monitor the corrosion behavior over the course of exposure. EIS was used to characterize corrosion because it is non-destructive, evaluates coating degradation, and helps to understand the mechanisms behind passivation. Some of the parameters used for EIS include frequency range and voltage amplitude. A frequency range of 100 kilohertz to 10 millihertz was used to capture the full electrochemical spectrum, ranging from high frequency ohmic resistance to low frequency charge transfer reactions necessary to calculate corrosion rates. We applied a 10 millivolt amplitude to ensure a linear response from the system while providing a high enough signal to noise ratio for accurate data collection. Due to the setup being limited to testing one sample at a time, the samples were tested sequentially. AIS helped us to collect quantitative data, but to get a visual representation of our corrosion, each samples were macro and micro imaged pre and post immersion testing. The macro images were taken with a phone and a light box, while the micro images were taken with the Keyence optical microscope in the IMO. Imaging was used to locate where the corrosion occurred. Now that you know how we conducted our research, Lucy will present what we found.
Okay. With that framework, we then examined how corrosion behavior changes over time across our single welded and ALD coated samples, with the focus on impedance trends, surface evolution, and weld effects. And we use EIS and optical microscopy to validate these electrochemical trends. So beginning with our baseline single samples, we took the impedance magnitude values at a frequency of 0.01 hertz and plotted it versus time to evaluate how the surface evolves during exposure. These impedance values were taken from the Bode plots of all of our samples after their 4 EIS measurements. We use 0.01 hertz because at a low frequency, the AC signal reflects the overall resistance to charge transfer across the surface of each sample. But looking at this plot, the impedance increased with time for all 4 of our single samples. And like Brylee mentioned, this indicates the formation of a passive oxide film, which improves corrosion resistance. There are some moments of what we think is repassivation, where the surface breaks down and repairs itself. We can see that in the 3D printed polished sample, which is indicated by the orange line. As you can see, the impedance values start to dip down and then increase up again. Our polished samples also consistently maintained higher impedance values, indicating a more stable and protective passive film. We think this is likely due to fewer surface defects, uniform oxide growth, and reduced corrosion initiation sites. Here are some images taken of our single samples on the Keyence microscope after the 21 days in the sodium chloride solution. As you can see, there is no visible corrosion, and this does reflect what we saw in our EIS data. For the welded samples, we observed significantly lower impedance than our single samples. This demonstrates that they are more susceptible to corrosion. There is still a slight increase in impedance over time, which means that the passive film is forming, but it's not stabilizing as effectively as our single samples. And again, the polished samples consistently had higher impedance than the as-is. Here are some images of our 3D welded to raw as-is sample after the 21 days of immersion. The image on the left shows corrosion products along the weld that confirm the electrochemical activity that we suspected from our EIS data. And the images on the right shows what the metal looks like after cleaning. There is some faint discoloration that was not there before. This is our 3D welded to wrought polished sample. And again, there's corrosion products along the weld, but there are markings that are more visible after cleaning. We were only able to collect 2 EIS measurements for each of our ALD samples, meaning they were only in the sodium chloride solution for a total of 7 days. So these are preliminary results, but both of our samples started at about the same impedance as our welded samples and followed a decreasing trend, which was not apparent in our other sample sets. This indicates issues with the passive film forming, but again, we are looking at a much shorter time range than our other samples. Here are some images of our ALD as is sample. The images on the right have very apparent corrosion in various locations along the weld. It's that like classic rusty color. And we also see apparent damage in our ALD polish sample. It's more faint, but it's along the weld at the very top of the sample. It kind of looks like a thin white line. And these physical results correspond with the limited EIS data that we were observing. This decrease in resistance we think is likely due to a non-uniform ALD coating at the weld because of the weld having heat-affected zones, internal stresses, and compositional gradients. There are a few observations and limitations worth noting. We observe crevice corrosion at the epoxy interface of many of our samples, as you can see in this picture, and this may have influenced the measured impedance responses. Variations in surface preparation and weld variability could likely contribute to differences in the passive film forming between samples, and it's important to note that impedance is a simplified metric and does not capture all aspects of corrosion mechanisms. So overall, our results demonstrate that the weld interface is the dominant factor in controlling corrosion behavior in additively manufactured to wrought stainless steel systems. Our welded samples consistently exhibited lower impedance compared to our single samples, and while surface finishing improved corrosion resistance, it did not eliminate the influence of the weld. Our ALD-coated samples showed an early decrease in impedance and visible corrosion. However, due to limited time, we cannot make any definitive conclusions about long-term mitigation. But overall, these findings confirm that the weld interface is the most susceptible region to degradation and governs corrosion behavior. Finally, we would like to thank the awesome professors, collaborators, labs, and organizations that helped to support and guide us through this project. Thank you.
Thank you. Any questions? Does anyone else have a question besides Amy? Okay, then I'll get back to you, Brandon.
All right, thank you for a nice presentation. You showed one of my absolutely favorite pictures in this picture, so thank you for doing that. It's the iron carbon phase diagram. It's the most famous in the world. I did not fully understand why you showed it. Maybe you can explain this to me. Thank you, that is a good thing. But you have stainless steel 316, something like 18, 10%, 18 chrome, 10 nickel, no carbon.
Yes.
So what do I learn from the phase diagram here regarding your weld seam?
So I got this to work finally. So what we're looking for is more of just the heat affected zone. We couldn't find a phase diagram that represents our exact composition, but our main focus of it was that the heat affected zone and the fusion zones are changing the microstructure, which happens in any alloy weld. So even though the bulk composition is the same, the chemistries and phases at the weld interface are going to be different. So we kind of use this phase diagram to represent that because we couldn't find one with our exact composition.
He gave me the microphone. Ha. How would you expect the heat affected zone to be different for 3D printed versus your wrought sample?
So our welding was done by a professional welder, and I did talk to him about this because he was kind of wondering the same thing. And what he noticed is that it welded the same as the wrought. He was like expecting it because it was additively manufactured. He was wondering if it was going to bubble differently or react differently in the weld. And he was really surprised and said that it behaved the same as the wrought because we did have wrought to wrought samples that were welded as well. And he said, other than the visual differences of the additively manufactured, it behaved the same.
Amy passed me the mic, so now I get to say something.
Yay.
How would we determine the size of a heat affected zone if we had the time to do so?
Future work. Also, maybe XPS or SEM?
Okay.
Brandon, is it quick? I'm gonna have to keep the mic from those people.
All right, good job, guys. I don't think this was specified, but what additive manufacturing technique was used for these samples?
Laser powder bed fusion.
Did you make them? Oh, from Brandon Corp.
Laser
Thank you.
powder bed fusion done by Brandon. Thank you.
Hi, everyone, and thank you so much for being here today. My name is Sydney, and I'm here with my teammates, Ellen and Suemy, and our project focuses on evaluating ASTM-based colorimetric methods for silica quantification in ultrapure water. I don't have the clicker. Okay. This project is sponsored by Micron Technology, who, as the NAND team previously mentioned, is a leading global semiconductor manufacturer based here in Boise, Idaho. We've been working closely with their chemistry lab to support research relating to their use of ultrapure water in semiconductor manufacturing. Micron is heavily reliant on ultrapure water. In the greater Boise area, civilian water use is about 20 million gallons per day, and we can compare this to Micron, who uses about 10 million gallons per day, and upon the completion of their expansion is projected to use about 50 million gallons per day. To manage this demand, Micron is working towards reclaiming 100% of their ultrapure water by 2030, which poses a new challenge for us of ensuring that all reclaimed water remains clean enough for manufacturing. Ultrapure water is used through the entire wafer fabrication process in steps such as cleaning, etching, and rinsing, so it must be completely dissolved or completely free, of all dissolved contaminants. Micron's wafers are made of silicon dioxide, and they can easily contaminate their ultrapure water supply during these steps, making silica a key impurity to control. Silica exists in both reactive and colloidal forms. Its reactive form behaves like a weak acid, making it easy for us to test with colorimetric methods. So that is the form that we focused on for this project. And even extremely small amounts of it can deposit onto a wafer surface and render the entire wafer useless. So we are trying to detect silica at a parts per billion and parts per trillion scale. And to put this into perspective, detecting silica in ultrapure water would be like trying to pinpoint the exact location of the MCMR on this map right here. Other methods do exist for detecting silica. However, we decided to go with the colorimetric method because it is simpler, less costly, and more accessible here to us on campus. To measure silica concentration, we used UV visible spectroscopy because it measures the intensity of a colored solution. It is based on this equation here, also known as Bier's law, which states that the absorbance A is proportional to the concentration C. This means that higher silica concentrations will produce higher absorbance values. The way it works is light at specific wavelengths is transmitted through a sample, as shown in the diagram there. And then our detector takes intensity measurements of our I naught and I terms, which we can then use to calculate the silica concentration in our solution. It is important to note that the detector does only measure light intensity, and it is agnostic to scattering and refraction, which can influence our measurement readings. This becomes especially important later when we discuss sources of measurement variability in our results section. A well-documented colorimetric method is the ASTM D859 standard, which can determine reactive silica concentrations within a range of 20 to 1,000 parts per billion. It involves a series of chemical reactions that eventually produce a measurable blue-colored complex. The first step is acidification, which converts all colloidal forms of silica into its reactive form. Next, ammonium molybdate is added, where it reacts with the reactive silica to form Kagan ions of silica molybdate complex. This complex structure can also react with phosphorus present in the solution, so oxalic acid is then introduced to remove any phosphate interferences. And finally, a reducing agent is added to convert the solution into a silica molybdenum blue complex, which can then be quantified with spectroscopy. For our experimental design, we kept this entire procedure constant, but compared two different reducing agents to determine which one gave us the most reliable results. And now I'm going to pass it over to Suemy to tell you about our goals and objectives.
Okay, now moving on to goals and objectives. The goal of this project was to evaluate two colorimetric methods for silica detection and identify which one will give us the lowest detection limit. And for our objectives, the first one is to conduct a literature review on existing colorimetric methods, many of which are decades old, highlighting the need to reassess these methods using modern equipment. The second objective is to test the ASTM-based method using two different reducing agents, ANSA and ascorbic acid. And ascorbic acid is a reducing agent that is used in another colorimetric method called EPA NERL 370.1. And finally, we wanted to compare both methods via error and statistical analysis. The method of standard addition, or MSA, is a quantitative technique where we determine the concentration of an unknown analyte in a sample. In this method, constant volumes of unknown are placed into different samples, and then increased volumes of the standard solution are added, and finally we dilute them to a fixed final volume. The instrument response for each sample is measured, and the instrument response is plotted against the volume of standard added, and this will give us a linear relationship described by y equals ms plus b. And to get the concentration of the unknown, we look at the x-intercept, which equals negative y-intercept divided by the slope. So for MS implementation in our experiments, we prepare a series of dilutions using ultra-pure water from the MilliQ system and sodium metasilicate. And we prepare 4 different standards of different concentrations, and one of them we treat them as the unknown. And we intentionally prepare the unknown at a known concentration level because we wanted to see if our results match. And that will give us a confirmation that our method and measurements were working correctly. And for sample preparation, we did some modifications to the standard MSA. We varied the concentration of the standards, but we kept the volume of them constant. And this will give us a plot that relates the instrument response with the concentration, and that will be a much easier way to calculate the concentration of the unknown. So for our results, our first set of samples, we use ANSA as a reducing agent, and as we can see in the image over here, it turned blue. And when we look at the full spectrum, we see absorbance peaks for two of our highest concentrations at 850 nanometers. And however, below that, we could not see any absorbance peaks, which means that our limit of detection could be between 10 and 100 ppb. On the other hand, with our second set of samples, we use ascorbic acid as our reducing agent, and instead of turning blue, it turned yellow. And we think that this happened because there was incomplete reduction. And when we look at the full spectrum, we don't see any absorbance peaks, which further confirms that we didn't complete, the reduction was incomplete. In other words, we didn't reach the endpoint for it to change colors. Now I'm gonna pass it to Elen to go over analysis and discussion.
Okay, so we used the data from our ANSA reductions and we plotted the instrument response versus the concentration of the added standards. And then we generated a trend line of this plot, and then we calculated the x-intercept to that trend line. From the x-intercept, we determined that the concentration of our unknown was measured at 42 parts per billion. While this is still in the same order of magnitude, it's still a factor of 4 off of what we expected at 10 parts per billion. This suggests that we cannot reliably detect silica at the concentration of 10 parts per billion. We didn't have enough time to collect enough data to have a large enough sample size to do statistical analysis, so we decided to do some error analysis instead. First thing we did was look at the random noise of the instrument, which is inversely proportional to the square root of the integration time of our measurements. We looked at the data from our blank, and we determined that the random noise is about 3 × 10⁻⁴ absorption units. And then we use the instrument response from our highest concentration of our sample, and we generated a table of theoretical values of instrument responses for lower concentrations. We compared this to the random noise to determine the lowest concentration we should theoretically be able to detect with this noise level. A good signal is at least 3 times the noise. We determined that we should theoretically be able to detect 10 parts per billion with this level of noise because our theoretical signal is still 10 times our noise level. So then we looked further into sources of error, and we realized that we have a significant variation in our baseline measurements that we weren't expecting to see. The baseline variation was about 1.6 times 10 to the negative 3. And this is over 50% of the signal that we should have been getting for the 10 part per billion sample. So this would, in theory, impact our ability to detect that low of a concentration. While we're not sure the exact cause of this baseline variation yet, we think that it could be due to scattering because the instrument's agnostic as to whether the reduction in intensity of the light is due to absorbance, scattering, or refraction. Different things may be able to cause different scattering in the sample, such as different speciation during the silica molybdate blue complex development. So in conclusion, we're able to detect silica using the ASTM-based method using an answer reducing agent down to 100 parts per billion. Our method detection limit is likely somewhere between 10 and 100 parts per billion, which is comparable to that of the ASTM's documented method detection limit of 20 parts per billion. While instrument precision was pretty high, our baseline error significantly reduced accuracy and therefore impacted our method detection limit. So in the future, we could try taking more measurements between 10 and 1,000 parts per billion of different concentrations, so we have more to produce a trend line with on our plot. And we could also take at least 3 measurements of each concentration so we could perform statistical analysis. We could also look into the cause of the baseline error and attempt to reduce or eliminate it. We could also investigate as to why our ascorbic acid did not work the way we expected it to. We could also try to increase the signal to noise ratio by either using a higher path length cuvette so we have a higher signal, or we can increase the integration time and then we can decrease the noise level. Finally, we'd like to thank our wonderful sponsors over at Micron Technology, as well as our faculty here at Boise State University for all of their amazing help with this project. Thank you.
I was just curious because you had it on a slide, but it went too quickly for me to see. What were the other techniques that you'd considered? I know you chose this one because it was the most accessible and the cheapest, but
Or the other. Wait. There. Oh, that's here.
and then I was just wondering,
Sorry.
Based on your results, like, what do you think for Micron for implementation, would it be worth it for them to look into one of these other techniques, given that you were running into problems seeing things at those low contaminant levels?
Yeah, I definitely think could be beneficial to look into other techniques. The reason that we didn't use these two, which are other forms of spectroscopy, is simply because one of them just didn't allow, it wasn't as sensitive as using a colorimetric method. And then they're also much more expensive. They require specialized equipment that we don't have access to here on Boise State, in Boise State. But yeah, I think it's worth looking into more, for sure.
Anyone else? Thank you.
All right, welcome everybody. My name is Scott Horton. I'm here with my classmates Jacob Olson and Blake Michelson. Our project is on determining the hygroscopicity of salts. Our sponsor was also Idaho National Laboratories. Our contact there is Kevin Tolman, and our BSU advisor is Brian Jaquez. INL was interested in this project because the rates of hygroscopicity for salts are not well known, and they also wanted to make sure that purity requirements and specifications were met for their testing. Some problems that we encountered throughout this project was found that testing methods were very inconsistent, and also that salts will take on moisture when they're left out in the open. So some needs for our project is we needed to have a controlled testing environment, a standardized testing method. We wanted to understand why salts absorb water and how long a salt could be left out before it's unusable for any type of testing. So for our goal, it is to determine the hygroscopicity of salts. In order to do so, first we needed to calculate the surface area and then determine the weight gain over time for our chosen salts, which were lithium chloride, a eutectic lithium chloride, potassium chloride, sodium chloride, potassium chloride, and cesium chloride. And finally, provide a chart of the salt hygroscopicities to our sponsor and advisor. So what is hygroscopicity? It's a material's tendency to absorb moisture from the surrounding air. And with that, it'll always have moisture uptake, which includes mass gain, also hydrolysis. And because there's moisture present on the material, it can cause corrosion. But knowing the hygroscopicity can lead to safer storage and handling. So there are two different uptake mechanisms when it comes to this, and they are adsorption and absorption. Well, adsorption, as you see on the left, it's the process in which molecules adhere to the surface of a material. And it can lead to absorption on the right, which is a process in which the material absorbs the molecules into its bulk, distributing them throughout the volume. So this graph shows how water content of a material can change with increasing relative humidity. So if we look at the lower humidity levels, the material remains in the adsorption region. But each salt has its own point where at certain temperatures and humidities reach a deliquescence relative humidity, denoted as the DRH, where the salt transitions from a limited surface adsorption to substantial liquid phase moisture uptake. And beyond that point, in the deliquescence region or absorption, water uptake increases significantly as humidity rises, which also indicates that a material is dissolving into water. So in order to understand the hygroscopicity, the need to know a salt surface area is important. The Vernier-Teller or Emmett-Teller method, or BET, is an analytical technique used to find specific surface area of solid materials. The method is based on physical adsorption of gas molecules onto a solid surface, and it extends the Langmuir absorption model from a single layer to multi-layer adsorption. The BET method also provides critical information about surface area, which strongly influences the adsorption capacity and material reactivity. And then when we go into the humidity control gravimetric analysis, or the HCGA, it tracks change in mass due to factors of relative humidity and temperature. So salt that's exposed to humidity increases in mass and moisture uptake. And I'll turn the time over to Jacob.
To round out the background section, we used an Arrhenius-based model to describe moisture uptake as a temperature-dependent process for our lithium chloride and eutectic salts above their deliquescence relative humidity. Like Scott said, once the salts are above their DRH, they transform into bulk diffusion rather than just surface adsorption. The main idea is that high temperature will increase the uptake rate, allowing accelerated testing to predict lower temperature performance. We are doing this because lithium and chloride in the eutectic have lower DRHs than 20% relative humidity, which is the lowest humidity level that the chamber can go. Switching over to the technical approach, we first wanted to show you just an overview of our entire project workflow. We start this work in Dr. Jay Quist's lab with the BET surface area analysis portion, and then we transfer over to Dr. Ackler's lab, where we do the humidity-controlled gravimetric testing, which consists of the vacuum oven dry, the exposure in the humidity chamber, and wetting at allotted periods of time. Taking a closer look at the BET procedure, the machine we used for this was the Quantification Nova 2200E series, and it consists of two main operational steps. The first is the degassing step. This prepares the surface for nitrogen adsorption. You put the sample in the test cell and into the heating mantle, and then you heat it up to 300 degrees Celsius under vacuum. This is going to remove physiabsorbed water, gases, and any other contaminants in the system. We then move it over to the analysis step where the sample is cooled to cryogenic conditions in the liquid nitrogen dewar. It's then exposed to gas nitrogen at controlled relative pressures, and the BET model calculates the surface area automatically from there. Switching over to our humidity-controlled gravimetric analysis, it consists of 3 main steps. The first is to measure the crucible mass and the initial dry salt mass. The second is to dry the samples in the vacuum oven to remove that residual moisture and any impurities, and then record the mass once again. And then the third is to expose the samples in the humidity chamber and record the time at fixed time intervals, or record the mass at fixed time intervals. And then to finish our technical approach, we wanted to do an experimental risk and error consideration section, and we came up with 6 main points. The first is convection bias from hot samples on the balance. The second is mass uncertainty from the balance. The third is relative humidity instability of the humidity chamber. The fourth is residual moisture left after oven drying. The fifth is handling materials or human error. And the sixth is temperature and relative humidity drift due to ambient exposure. Now, moving into our results data tables, this first one is the surface area analysis. As you can see from our surface area values, most of them hover between 0.13 to 0.25 meters squared per gram. These are relatively believable values in accordance with literature. However, it's important to note that there's not one set in stone value because different salt manufacturers have different purities and salt specifications. The RSD, or relative standard deviation, is useful here because the absolute means of these samples are very small, which means that the very small measurement differences appear large proportionally. The high RSD means that the measurements are very noisy, and some of the small differences in the results can be reflected in the powder packing, sample heterogeneity, and low area BET measurement sensitivity. Another important observation is that our cesium chloride values have a completely different magnitude and should be approached with caution. However, it's important to note that nothing in the testing procedure changed between any of the salts. Moving forward, we have our humidity-controlled gravimetric analysis data tables with our 30% relative humidity testing on the left and our 40% on the right. These salts were hygroscopically ranked H1 through H5, with H1 being the highest rate of hygroscopicity. As you can see, for the lithium chloride and the eutectic, they are above their deliquescence point, which is why their water uptake is significantly larger than the other 3. And once they're above their deliquescence point, their behavior is as you would expect. With increasing temperature and humidity, they have a substantial increase in the weight gained. For the sodium, potassium, and cesium salts that are below their deliquescence point, the measurements for this are basically negligible and can be due to surface adsorption or measurement error. Because they're below their deliquescence point, we did deliquescence point specific testing, which Blake will talk about a little bit more in our analysis section. And finally, we have our surface area versus weight gain. This table correlates surface area with relative humidity with the dry salt mass. And there's 2 main points that we can take away from it. The first point is, as you would expect, with increasing relative humidity and increasing salt mass, there's an increase in the mean water gain. But the second and more important part is, as you can see, the salt has a higher surface area, or the eutectic has a higher surface area, but a lower water gain. That tells us that for the surface adsorption portion of this process, the surface area is really important, but once the process transforms into bulk diffusion, the salt composition itself is the driving factor in this water uptake. Next, I'll hand it over to Blake to have a further discussion of the analysis of our results.
All right, so as Jacob mentioned previously, we're utilizing the Arrhenius equation for our salts, specifically for lithium chloride and our eutectic. However, how do we know if the Arrhenius equation is viable for our salts? So what we did is we rearranged the equation, and then we plotted out the inverse of temperature versus the natural log of K, K being our mass percent gain. And if the plot is linear, then we know that it is viable, in which case it is very linear. So moving forward with lithium chloride and our eutectic, we plotted out the temperature in Celsius versus our weight percent gain. We have the points on each graph for 30% relative humidity on the left and 40% relative humidity on the right. Our points are 40, 50, 60, and 70 degrees Celsius. And then utilizing these points in the graph, we are able to extrapolate that at 22 degrees Celsius for lithium chloride and our eutectic, the pink dots are the lithium chloride and the eutectic is the orange, what their percent gain is. They're on the left side of each graph. So this is great for lithium chloride and eutectic, but what about our other salts, our cesium, potassium, and sodium chloride? What we need to figure out is that if they do not deliquesce at 30 and 40% relative humidity, when do they deliquesce? So an important note is that for our humidity chamber, it is unable to go below 40 degrees Celsius. However, we do know that as temperature decreases, the deliquescence point increases. In other words, if we know that sodium chloride does not deliquesce below 75% at 40 degrees Celsius, then it absolutely won't at 22 degrees Celsius. With this in mind, we did deliquescence testing, and we found that the deliquescence point is somewhere between 0 and 20% for lithium chloride and eutectic. It is between 75 and 85 for sodium chloride, somewhere above 90% for potassium chloride, and between 60 and 70% for cesium chloride. So due to a lack of time on experimentation, we couldn't go down all the avenues we wish to. However, we hope that in future work, whoever follows after will be able to go down the routes that we wish to, such as determining the time dependency. We can tell you how much weight gain there was at different temperatures for 40 minutes, but we don't know for 20, 10, or 5 minutes on, say, a countertop. For narrowing down the deliquescence points, we have a range, but it'd be fantastic if future work could look further into that. And also investigating other salts. Initially, we wished to look at strontium and cerium chloride in addition to our 5 salts, but unfortunately don't have the time to do so. So in conclusion, we found that there were 2 water uptake methods for salts. There's adsorption and bulk diffusion. We found that lithium chloride and eutectic underwent bulk diffusion at relatively low humidities, while cesium, potassium, and sodium chloride would undergo adsorption up to relatively high humidities. And for countertop experimentation, though this is an overgeneralization, we can consider working with lithium chloride and the eutectic as fairly dangerous, while potassium, cesium, and sodium chloride is relatively safe if you're fine with up to 0.2% weight percent gain for your salts. We'd like to acknowledge Kevin Tolman with Idaho National Laboratory, as well as Herold Ackler and Brian Jaquest with Boise State University for all their fantastic help with our project. Here are references, and thank you very much for listening.
Thank you. So time constraints were interesting for this project because I would point out that nice fancy vacuum oven you saw in their original plot. That showed up in my lab last Wednesday. Other things were not so late, but purchasing problem. Any questions?
This is a talk where I would have liked to see a phase diagram. Where's the eutectic? What's the composition of the eutectic?
59% lithium chloride, 41% potassium chloride.
Thank you.
So the lithium chloride that you're comparing that eutectic to had the lower surface area, but absorbed more water. And the eutectic is lithium chloride and the potassium chloride. Is the difference in water uptake attributable to just the percentages of lithium chloride versus potassium chloride? Is it the weighted average of those two?
It's actually really similar. That's my assumption, is that it's just the lithium chloride. However, we didn't really go in depth into researching whether that was the only cause or if there are other factors at different temperatures, different relative humidities, and so on. But that's exactly my thought process.
Anything else? Y'all want cake, don't you? Well, right on time. Thank you, everyone. I really appreciate the time you took today.